Hello, this is Nathan Joslin. This is the CodeJacer shortest path. So first we're going to talk about how I adapted the adjacency pixel graph to code the generative scene finder pixel graph.neighbors. So the main thing I noticed in the adjacency class was that they had the same conceptual logic for finding the neighbors, where that was a right up, right middle, and right down as per the spec. And so I took that idea and I applied it to the neighbors method in the generative scene finder, because in the generative scene finder, unlike the adjacency, we don't have a neighbors instance, meaning that every time we want to know the neighbors, we actually have to manually calculate that based off the 3 different cases. And these cases again are right up, right middle, and right down. Now the main difference, as you can see here, is that in the pixels class for the adjacency, we actually have a neighbors instance, meaning that off construction of a pixel and then on the adjacency, it already has access to to its neighbors, so you can just call it. There's no need to compute it manually via a method. You can just call it and get the neighbors. Now, of course, these two things have a lot of similarities. One of them I just discussed, which was the neighbors computation, the neighbors logic. The second similarity was that they both follow the same DAG structure, meaning that they're both directed acyclic DAG structure. So yeah, those are the two main differences or similarities. We can see that right here. So they follow this same kind of graph, not this one exactly, but this particular one. So next, we're going to be discussing dynamic programming and the implementation. So the dynamic table or the dynamic programming used a table instead of a graph to fill out the same kind of idea as in the previous two methods. And so to do so, what we did here is to fill this table, we went column by column. And for each pixel, the algorithm computed its energy and added the minimum accumulated seam cost from the previous column among its valid previous pixel. So whereas in the generative and the adjacency method or classes where we did the logic for computing the neighbors was right up, right middle, right down, here we're going to be looking left up, left, and left down, because the difference in dynamic programming is that we start at a goal and we work backwards from there. Yeah. So the next question is, how does it select the minimum from its neighbors? The minimum is selected using repeated math min comparison. We start with a double min instance, or we initialize a double min value here, which starts at infinity, and then we compare it to each different case. So each previous pixel. So you can see dpx minus 1, dpx minus 1 middle right there. So that's going to be left right there, the first one. And then we're going to do left down, and we're going to do left up. And so the reason we start min pre to infinity is because this allows us so we can get a more accurate min value, because if we started at something like 0 or -1, we would never get an accurate minimum value between that and the previous value or previous pixel. So we start at positive infinity, guaranteeing that we're always going to get the minimum value if it is true. Next, we're going to discuss the code for finding the seam with the lowest energy cost. So after filling the DP table, the algorithm scans the rightmost column to find the minimum accumulated seam cost. And the row where the minimum occurred is the endpoint of the shortest seam, or the most optimal seam. So then the next question is, how is the first minimum found in the rightmost column? Well, we just answered that, where the algorithm scans the rightmost column to find the minimum accumulated seam, and the row where the minimum occurs is the endpoint of the seam. So then it's afterwards, how do we find the lowest energy predecessor? Well, after we do all that, the seam has been reconstructed by backtracking. So we go leftward. So at each column, the algorithm selects the predecessor. So this is the left up, left middle, or left down with the smallest DP values. And because the DP table stores the most optimal subproblem results, this guarantees correctness every single time. And so ultimately, the method returns a list of the row indices representing the horizontal seam from left to right. But because we're starting at the end, we have to reverse the list at the end of scanning through and finding the seams.